All right, today what we're focusing on is identifying and continuing patterns. Again, it seems to be a pattern here. Okay, I can write recursive formula, and we're going to use that formula to calculate the nth term. Notice recursive is not the same as explicit. We're going to be writing both today just to get our practice. So for the last several days, we've been talking about this explicit formula. The explicit formula allows for direct computation, meaning we can do it immediately. We don't have to find all the other things before it, of any term in the sequence. In other words, it allows us to determine the nth term, like what we've been doing. Okay, so here is our sequence for arithmetic in both function notation and sequence notation. Then over here we've got the geometric ones. Notice the n-1 exponent is the biggest thing that's different. Okay. All right, and let's keep moving. So today we'll be focusing on something called the recursive formula. Recursive formula comes from the word recursion, or reoccurring, meaning it's happening every single time. Recursion is the process of choosing a starting term and repeatedly applying the same process. In other words, adding or subtracting the same thing every time, or multiplying or dividing by the same thing every time. That's what we've been doing. The recursive formula will always have two parts: an indicated term. So this could be like a sub 1 equals, and then you'll have a number. Or you could have a sub 20 equals, and it will have a given number, okay? In which to start the process. The process is happening to get to the next number. So here, the recursive formula for the arithmetic sequence. So we've got a sub 1 equals a number. X is the first term, or the starting term of your sequence. A sub n is now. In other words, whatever term you were looking for. A sub n-1 is the term before. And d is the common difference. So here's an example of a sequence. We've got an arithmetic sequence. It goes 3, 5, 7, 9, 11. So every single time it's just adding 2, right? So if it's just adding 2 every single time, my first term, so that's the first thing I need to identify, is 3. Then my next term will be the term before it. That's all this. This is a fancy way of writing the term before. That's all that is. Fancy way of writing that. And we're going to add 2. Okay? This is the recursive formula for that sequence. So let's take a look at this one. So we're going to use this recursive formula to find the 20th sequence. So here's our first one. We're adding 2 every single time. So a sub 1 equals 3. A sub 2 is 5. A sub 3 is 7. A sub 4 is 9. A sub 5 is 11. 6 is 13. The 7th term is 15. The 8th term is 17. The 9th term is 21. The 10th term is 23. You'll notice I went ahead and finished the rest of them because that was a lot. So by the time you get to the 20th term, you'll notice we have done a whole lot of math. And we end up with the final term of 43. That's kind of cool. All right, so now let's look at the recursive formula with the geometric sequence. You always start with your first term, whatever number that is, it's your first term. Then a sub n is right now. A sub n-1 is the term before, and you'll notice this time we are multiplying by a rate because we're multiplying every single time. Okay, and so here's our geometric sequence. It goes 5, 15, 45, 135, 405. It seems that every single time we are multiplying by 3. So it wants us to find the 10th term of the sequence. So we've already found the 5th. So we have the first is 5. The second is 15. The third is 45. The fourth is 135. The fifth is 405. The sixth is 1,215. The seventh is 3,645. The eighth is 10,935. The ninth is 32,805. And finally, the 10th, what we wanted to know in the first place, is 98,415. Ta-da! Do you see how much work this is when we use the recursive formula? This is the entire reason why the explicit formula came about, because no one wanted to continue to do things like that. So we're going to write the recursive formula for the following two. So the first thing we need to do for the recursive formula, define a term. So term 1 is -3. So I'm going to do a sub 1 equals -3. Now our formula for whenever we want a p is going to be something else. So we're going to have a sub n equals a sub n minus 1, or the number before it. This goes -3 to -6, -6 to -9, -9 to -12, and -12 to -15. So this seems to be subtracting 3 every single time. So I'm going to subtract 3. And that is my recursive formula. So let's take a look at this next one. Over here, we're going to define our first term. So I'm going to go ahead and go to my first term. Notice my first term was not the very first number written. It was the first term. So a sub 1 equals -2. And it goes from -8 to positive 4 to -2, 2 to 1, and then 1 to -1/2. So it's alternating. So we seem to be multiplying by a negative. Oh, wait. So we've got our a sub n minus 1. And we seem to be alternating between signs. So we're actually multiplying by a negative number. So let's figure out what that negative number is. We went 8, 4, 2, 1, 1/2. We seem to be dividing by 2. So we're actually multiplying by -1/2. That's what's happening every single time. Okay? And then this is my recursive formula for that one. All right, so let's try this a couple more times. So for each of the following sequences, we're going to find the common difference or ratio, write the recursive formula, just like the one we just learned, and write the explicit formula. So we're going to end up writing both formulas, okay? And notice you're given a little bit more space on B because you have to write 2 parts for that formula, right? Okay, so we're going to find the common difference or ratio first. So this goes from 63 to 59, 59 to 55, and 55 to 51. This seems to be subtracting 4 every single time. So we have a common difference of -4. So let's write our recursive formula. For the recursive formula, we need to define a term. So I just picked the first one, and I'm going to do 63. Then, this means that we're going to, where we are at is made by the term before, and we are subtracting 4 every single time. So here is the recursive formula. So now let's make the explicit formula. So the explicit formula says a sub n equals, we're going to take our first term, so 63, then we are subtracting 4 every single time, and because this is the explicit formula, we still have that n minus 1 piece, but now it's part of the equation, not just saying, hey, it's the number before. All right, let's go ahead and try the next one. So in the next one, this goes 1 to 8, 8 to 15, and 15 to 22. This one seems to be adding 7 every single time. So this one is also a common difference of +7. So that means our recursive formula, we have to define a term first. So a sub 1 is 1. And then we've got our next term will be the term before, so a sub n minus 1. And then this time we are adding 7 every single time. So there's my recursive formula. And then my explicit formula, we've got a sub n equals, we're going to take our first number, so 1. And then every single time we are adding 7. And then because we're adding, the n minus 1 goes in parentheses next to the 7. Okay, I want you guys to go ahead and try this one out. And this one. And this one. Once you're done with that, go ahead and write your recap.